Millikan carried out series of experiments and demonstrated discrete nature of electric charge. He measured the charge on electron. The experimental setup consists of constant temperature oil bath, and there are two circular metallic discs. Okay, so I'm drawing. So there are two circular metallic discs or plates. The experiment actually consists of a circular hollow chamber, okay, double walled circular hollow chamber, and there are two circular metallic discs or plate, okay, with upper discs or upper plate containing small pinhole so that oil drop can get in the region between the plates. So we have this, okay. So there are two circular metallic discs or plate with upper plate containing small pinhole so that oil can pass through it, okay, and the discs or plates are 20 centimeter in diameter and are 1.6 centimeter apart. So the distance between the discs or plates are 1.6 centimeter apart, and a high potential difference, okay, we can see a high potential difference of about 10,000 volt can be applied between the plates or discs, and oil is sprayed inside this chamber with the help of atomizer, and the oil is non-volatile so that we can carry experiment for longer time, and we can take clock oil in order to carry experiment, okay. Now there are three windows in this experimental setup. Through one window, X-ray is allowed to pass in the region between the plates, and through another window, okay, light is allowed to pass inside the chamber so that we can absorb oil drop, and third window, which is not shown in the diagram, is fitted with telescope, and we can observe oil drop with the help of telescope. The spacing between the plates is strongly illuminated by light, and small oil drops are produced, okay, by atomizer. The drops moves down and some of them enters the region Okay, they enters the region, this region, okay, enters the region between the plates through small hole. So there is a small hole or pinhole made at the upper plate. So the upper plate consists of small hole so that oil drop can be passed through it. The drops are generally charged by friction, okay, during the spraying process. During the spraying process, because if we look into this diagram, okay, let's say this is the atomizer, and when the atomizer or when the oil is sprayed with the help of atomizer, and due to the friction between the surface of the atomizer and oil, the oil drops get charged by friction, and since the X-ray is passed inside the chamber, the air molecules in the region between the plates gets ionized, due to which fresh ions are produced, so that the drops picks up additional charges, that is positive and negative. So I'm writing, by help of X-ray, fresh ions can be produced so that drops can pick up extra charges, that is positive and negative. So we find this. Now, for observation purpose, we consider negatively charged single oil drop and study its motion under gravity and under the influence of electric field. So I'm writing, for observation, we consider negatively charged single oil drop and study its motion, okay, one, under gravity alone, second, under electric field. Consider or discuss motion under gravity, that is, there is no electric field. Clear? So there is no electric field. Now what we find, so as the oil drop moves in the presence of gravity, suppose this is oil drop, okay, falling under the influence of gravity, so we find the weight of oil drop acting vertically downward, and since the motion of the oil drop is downward, so that the resisting force, that is R, acts opposite to the motion, and bind force acts opposite to the weight. Okay, so these are the force or forces acting on oil drop falling freely under the influence of gravity. So let me write in this way. Okay, as the oil drop falls under the influence of gravity alone, okay, then an opposing force due to viscous drag, okay, since there are air molecules present, okay, there are air molecules present in the space between the plates, and the air molecules offer opposing force, that is viscous force or viscous drag to the oil drop. So I'm writing, then an opposing force due to viscous drag, why? This is due to air, okay, viscous drag is due to air, acts on the oil drop. So we find this, okay, opposing force, that is viscous drag, acts on the oil drop. So we find this. And what we find is that the opposing force or the resisting force, okay, we find the opposing force or resisting force is proportional to the velocity of oil drop. So I'm writing in this way, okay. Let us denote the opposing force by symbol R, okay. This is proportional to the velocity of oil drop. So we can write R equals some constant, and let the constant be K, times V. So let's call it equation number 1, where K, this is the constant of proportionality, okay. The value of K as given by Stokes, okay, is K equals 6 pi eta R, okay. Therefore, resisting force R equals 6 pi eta R V. And this equation is called Stokes' law. This is called Stokes' law. So in this equation, eta, okay, this is the coefficient of viscosity, okay. So this is the coefficient of viscosity of the resisting medium. So in this case, the resisting medium is air. So eta is the coefficient of viscosity of air, and small r is the radius of oil drop. So we have this. Clear? Now, the force acting on the oil drop. So what we find, let me write in this way, the forces acting on oil drops are 1, okay, its weight, W equals mg, okay, so we have this. Second, the resisting force R, and this is due to the viscous medium or air present between the plates, okay. And third, the buoyant force, B, due to air, and buoyant force is opposite to the weight. So what we find, the oil drop is moving down, okay, so it has downward acceleration. So let me write in this way, let F be the resultant downward force. Therefore, F equals W minus B minus R. Let us call it equation number 2. So what we find, the oil drop is moving downward in the presence of gravity, so that there is resultant force acting in downward direction. Clear? Or it is accelerating in downward direction. So the resultant force is F. Now, from 1 and 2, okay, from 1 and 2, we can write F equals W minus B minus K times V. So we have this. Now, initially, okay, velocity is 0 if we take the velocity of oil drop 0, okay. Then what we find, resisting force, that is R is 0. Clear? So if this is 0, then from this equation we can write resultant downward force, that is F equals W minus B. So we get this, okay, so we get this. Clear? So let me erase this now. So I'm writing over here, okay. We have R equals, resisting force R equals K times velocity of oil drop. Now, the drop, okay, has initial, okay, downward acceleration. So as the oil drop moves downwards, the velocity increases. Clear? So what we find, as the oil drop moves downward, velocity increases, and if velocity increases, then from this relation, okay, resisting force increases. So the velocity increases and resisting force increases. So we have this, and reaches a value, okay, it reaches a value at which resultant force, okay, that is F equals 0. So if the resultant force is 0, then the oil drop falls with constant velocity called terminal velocity. So I'm writing the drop then fall with constant velocity called terminal velocity. And let us denote terminal velocity in the presence of gravity only, or under the motion of gravity only, by the symbol Vg. So this is terminal velocity of oil drop falling under the influence of gravity only. So we have this, okay. So I'm erasing this. Now, therefore, we can write F equals 0 when V equals Vg, that is when velocity equals terminal velocity. So from this equation, okay, so from this equation we can write, from second we can write, okay, F is 0, W minus B minus R, and we know R is K times V. Now we have to replace V by Vg. So therefore we can write K times Vg. Clear? So we can write W minus B equals K times Vg, and let us call it relation number or equation number 3. So we have this. Now let us suppose, okay, so first let us denote the terminal velocity, or after attaining the terminal velocity, okay, we have this, okay. Drop is moving with constant velocity, that is Vg, okay, when the resultant force, that is F equals 0. Now let rho be the density of oil and sigma be the density of air, and we know density equals mass by volume, okay, we know this. Therefore W equals mass of oil drop times small g, and mass is density, okay. So density for oil is rho, and volume of oil drop is 4/3 pi RQ, and we have G. So we can write 4/3 pi RQ rho G, and buoyant force B equals, okay, so we have to find bind force. So what we find is that the oil drop replaces the same volume of air, isn't it? So the volume and bind force is for air. We are calculating bind force for air, so that the volume of air displaced by oil drop is 4/3 pi r cube. Okay, that is the volume of air displaced equals to the volume of the oil drop, and density for air is sigma, and we have G. Okay, so we have this. Therefore, from 3 we can write 4/3 pi r power 3 rho G minus 4/3 pi r cube sigma times G equals K, and we know K is 6 pi eta r. Okay, this is in accordance with Stokes. So K is 6 pi eta r, and we have Vz. Now okay, I'm rewriting this equation, okay, over here. 4/3 pi r cube rho G minus 4/3 pi r cube sigma G equals 6 pi eta r Vz. So we have this. So we have to simplify this, okay. So this cancels out, okay. So we get 2/3 r square rho minus sigma G equals 3 eta Vz. So r square equals 9/2 eta Vz by rho minus sigma, and we have G, okay. So therefore r equals under root 9/2 eta Vz by bracket rho minus sigma bracket close G. So this expression gives the radius, okay. This gives the radius of the oil drop. So we have this. Now we can find the value of K, and we know K equals 6 pi eta r, okay. So we have this. So K equals 6 pi eta, and r is this, okay. So 9/2 eta Vz by rho minus sigma, and we have G, and whole power 1/2. So we have this. Clear? Now we can write K equals, so 6, and this 9 comes out of, so when it comes out it becomes 3, okay. We can take this 9 out of the root. So we get 18, okay? 18 pi, and let us take this eta inside the square root, okay? So this becomes eta power 3 Vz by 2 rho minus sigma, and we have z, okay? And whole power is half. So this is the value of k. Clear? This is the value of k. So let me write the equations, okay, over here. So this is motion in gravity, okay? So I'm writing this is in gravity. This is motion in gravity. So we have this. Next, we study motion under electric field, okay? Motion under electric field. Now, potential difference is applied between the plates, clear? Such that the upper plate is positively charged and lower plate is negatively charged. So I'm drawing over here. Upper plate is positively charged and lower plate is negatively charged, and we have negatively charged oil drop. So we are going to study the motion of negatively charged oil drop in the presence of electric field. So this is to be noted, okay? So what we find? So let's say, let the electric field be applied between the plates, okay? Let me erase this also, okay, so that we do not get confused. So what we find now, the oil drop moves upward, okay, because the upper plate is positively charged with upper plate positive and lower plate negative, okay? So upper plate is positively charged and lower plate is negatively charged. So what we find, the oil drop moves towards the upper plate, clear? The oil drop moves towards the upper plate. So we find this, clear? So what we find, the motion of oil drop, okay? So let me draw in this way. The motion of oil drop, the motion is upward, clear? So the motion is upward and the weight of oil drop acts vertically downward, and if the motion is upward, the resisting force acts opposite to the motion. Okay, so this is resisting force in the presence of, or when the oil drop is moving under the influence of electric field. So previously we have denoted resisting force by the symbol R when the oil drop was moving under the influence of gravity alone. Now, since the motion of oil drop is upward, the resisting force acts opposite to the motion. So let us denote the resisting force by the symbol R dash. So R dash is acting in downward direction. Now, the bind force acts opposite to the weight. Okay. Now, the oil drop also experiences electric force, okay, in the presence of electric field, and we know electric field is directed from upper to lower plate, and in the presence of electric field, okay, the negatively charged oil drop experiences electric force. So this is the electric force. Clear? So this is electric force. So electric force is directed opposite to the electric field. So electric field is acting in downward direction. So electric force is acting in upward direction. So we have this. Clear? Now, as I said earlier, okay, these are the forces. Okay, bind force, electric force, resisting force, and weight mg acting on the negatively charged oil drop moving under the influence of electric field. Clear? So we need to note this. Okay, so let me write. In the presence of, okay, so I'm writing in this way. In the presence of electric field, the drop experience force, that is F equals, let's say QE. Okay, this is in magnitude, and this force is directed upward. We can see it is acting in upward direction, and the velocity of rise, since the drop is moving upward, depends on charge Q. So we have this. Now we need to find the resultant force on the drop while it is rising. Okay, so let F be the resultant force on drop while it is rising. Okay, so therefore we can write F equals, now since the motion is in upward direction, so we write QE plus B bind force minus W minus R dash. Okay, so this is resisting force. Keep in mind, this is resisting force. Now what we do is that F equals QE, okay, minus So let us do simple mathematical, okay, manipulation. So I'm doing this minus, this is K times V, okay, because resisting force is proportional to the velocity. Okay, we have this. Now, when terminal velocity, let's say terminal velocity in the presence of electric field B VE, okay, so this is terminal velocity in the presence of electric field. Clear? When terminal velocity VE is reached, okay, then resultant force is 0. So therefore, this equation, okay, becomes 0 equals QE minus W minus B, okay, minus K times VE. So when terminal velocity is attained, then the resultant force is 0. So we can write, on rearranging, QE equals W minus B, okay, plus K times VE. So we get this. Now, in the presence of gravity, okay, so under motion under gravity, so we were having this, okay, resultant force F. So we are having this resultant force F equals W minus B minus R. So we are having this. Now when terminal velocity Vz is attained, then F equals 0. So therefore, W minus B equals R. So W minus B equals R, and R is K times Vz. So we have this, okay. So what we do, this W minus B is replaced by K times Vz. Clear? So QE equals K times Vz plus K times VE. Clear? We have this. Now Q equals, K is common, Vz plus VE divided by E. So we have this. Now let us put the value of K, okay. So Q equals, K is this, okay, 18 pi, and we have eta Q Vz divided by 2 rho minus sigma G whole power half, and we have Vz plus VE divided by E. So on rearranging or on further simplifying, okay, so let me write over here. So let me write this equation over here. Q equals 18 pi, and if I take eta, okay, outside the square root, then we have 1 eta outside, okay, divided by E. So we have this eta, okay, Vz divided by 2 rho minus sigma g whole power half, clear, and Vz plus Ve. So this is the required expression, okay, for charge on oil drop, and using different values of electric field, okay, or potential difference for various drops of different size, it was found that charge on oil drop is practically a whole number, that is Q equals Ne. So I repeat once again, using different values of electric field or potential difference for various drops of different size, it was found that charge on drop is practically a whole number, that is Q equals Ne. So we can conclude that charge is multiple of basic or fundamental charge. So charge is multiple of basic or fundamental charge.